Hello everyone, welcome to Enigma channel, and for today's video we are going to solve this problem, an integration which consists of an nested square root. So as we can see, we have an integral given by integral of x times square root of x raised to ln x times cube root of x raised to ln of squared x times fourth root of x raised to ln of cube x times fifth root and etc. from 0 to 2 dx. So as we can see, this is a tough one to solve, but with the help of course of the known techniques that we have, we can easily solve this problem. So feel free to pause the video if you wanted to try this first, and let me show you the solution afterwards. So right now, let's start with solving this problem. So we can see that this nested radicals. Sorry, the nested radicals are able to be are able to represent in terms of exponents. So right now, we just wanted to simplify this problem by doing that step. So right now, let us first write, of course. So we write this in terms of exponents instead of having a radical, because it would be difficult for us to see the pattern that is happening if we have this kind of form. So right now, let us write. So x is the first term, and as we can see in this case, in this one, we have a x raised to ln x, but it is a square root. So square root means raised to 1/2. That's why we have to multiply this by x raised to ln of x and divided by 2 all over 2. And of course, since we have another radical here that is inside of also of the square root, then since this is 3, then this is half. So we have a like this. So we have ln. So since this is ln squared, no, ln squared and x, ln squared of x. So that's what it means, all over 3 times 2. So why do we multiply it by 2? Because it is inside the square root. So it is like saying na if you have square root and then cube root sa loob, diba? Inside. So you have, so since this is 2, then all you have to do is to first, this is raised to 1/3, and since raised to 1/3 and multiply by something, so this is raised to 1/2. So let's say this is a, so this is a, and then raised to 1/2. Then by the rules of exponent, this is multiplication, right? So we have to multiply this. So this is now 1 times 3 times 2. 1 over 3 times 2. So this is equivalent to a raised to 1 over 6. Did you get it? So if you do, so let me proceed with the solution. So right now, by continuing the manner of rewriting those terms, we get the next term as ln cube of x all over 4 times 3 times 2, then etc. So the next terms are, of course, this is an infinite product because there is a dots here that indicates that it is continuously nesting, so therefore we have an infinite product in this case. So let me enclose this by bracket so that it is clear for us to see that this is an infinite product. So right now I want you to see that since these terms are of the same basis, so this and this, so and etc., so it means that we can just add those exponents of them. So right now, since this is a rule, right, because we know from the algebra we have, let's say this is 2 times a raised to 3, so this is just equivalent to 2 plus 3, right, and 2 plus 3 is 5. So when we multiply the terms of the same base, and if they have exponents, then we can just add the exponents of them. Okay, so right now what I'm going to do is to add the exponents. So writing again, we have 0 to 2 and x raised to, of course this is 1, no, this is visible, so this is, let me write, so this is 1 plus ln of x all over 2 times 1. So do you agree that I can write 2 as 2 times 1? Yes, of course you should agree, because 2 times 1 is just 2, because 1 is just an identity element in multiplication. So next term is ln squared of x all over 3 times 2 times 1, and the fourth term is we have ln cube of x 4 times 3 times 2 then times 1, and etc. So this is now an infinite series, right? So since this is an infinite series, we wanted to find the pattern that is taking place in this case. So as we can see, since the first term is 1, and we can say also that this is all equals to ln x raised to 0, because any number raised to 0 is just 1, no? So right now, of course, we can also say that this is 0 factorial. So 0 factorial is also 1, right? So you can prove that using the factorial's definition. So this is just 1. And as for the second term, we have, so this is the first term, no? First term. And as for the second term, we have ln x raised to 1 all over 2 factorial. Since 2 times 1 is just 2 factorial, and etc., we have ln x squared all over 3 factorial, because 3 times 2 times 1 is just 3 factorial, and so on. So can you now see the pattern? Can you see the pattern that's taking place? So if you do, then you would agree with me that the pattern here is indeed ln x raised to n minus 1 all over n factorial. So why this is true? Because we can see that the pattern in this infinite series is this, and if we input some value from 1 or from 1, we can say that 1 minus 1 is 0, and this is supposed to be 1. So in order to agree with the general formula, so this is supposed to be 1 factorial. So there's no violation that is happening because 0 factorial is equals to 1 factorial. So right now this is the first term, and then this is the second term, this is the third term, and so on and so forth. So this is the nth term. So this is the nth term. So if you input the values of 1, 2, 3, etc., we can see that the first term, the second term, the third term, this nth term gives us all those terms that in the infinite series. Thus, we can now write the series into a single summation that will make us less hassled by the problem. That will make the problem easier. So right now, by doing so, let us first write so by doing so, don't forget so by doing so, we have, what do we have right now is an infinite series. So this is now raised to an infinite series. So when writing an infinite series, you will just put a sigma symbol, and below that you have to write the oops. So this is n equals, so this is 1, right? Because from the previous step that we do, the pattern, the sequence start from n equals 1, and right now we wanted to put the general pattern that we have, which is ln of x raised to n minus 1 divided by n factorial. Of course, so this one has a closed form. So from if you will study the expansion, or particularly the Maclaurin series or the Taylor series, so you will see the closed form of this formula of this summation. So right now, so let me rewrite again. So from the Maclaurin series, this is for all x. So so this is for all x, even the complex numbers or the real numbers. Right now, using this formula, we can do some manipulation that will allow us to solve the series. given so this is ln x raised to again n minus 1 and divided by n factorial. So right now, as we can see, since we have n minus 1 raised to n minus 1, we can put 1 over ln x outside this series because ln x or x term is not important inside the series, so we can just factor it out because it has nothing to do with the variable that is focused in the series. So it is like a constant in this case. So 1 over ln x, because ln x raised to negative 1 is just 1 over ln x, and n equals 1 to positive infinity, and this is now ln x raised to n all over n factorial. And right now this is just equivalent to, since we do not have a zero term where n is equal to 0, then we have to we have to adjust this series first in order to achieve what we want. So this is just, so can you agree that this is just negative 1 or negative ln raised to 0 x of x ln of x raised to 0 divided by 0 factorial plus this series, but right now we have n equals 0 because we have a 0 term in the front before the sum, and we have ln x raised to n all over n factorial. So can you agree that these are equal? Of course yes, because since we do not have the first term or zero term, so we just assume that there must be a term that like this, so that this the index of this series becomes n equals 0 instead of n equals 1, so that we can use the formula. So since we have a negative sign here because initially we have n equals 1, so we do not have n equals 0. So if you will expand this series, you will see that these both series are equal, these both expression are equal. So right now, since this is just 1, then we must say that also this is also by Maclaurin series, this is just e raised to ln of x, but ln of x is just x, right? So right now we can now say that this whole thing is just x minus 1 divided by ln of x. Easy, right? So right now, by going back to the integration problem, we can now substitute this value of infinite series into x minus 1. Oops, sorry, this is supposed to be 2. So x raised to what? X minus 1 divided by ln x. Right now, do you think this integral is pretty hard to solve? So if you say yes, actually this is not that hard, because as we can see from this formula, e raised to ln x is just equals to x. So we can rewrite this x into e raised to ln x for further simplification. So this is just e raised to ln x, and then of course we have to raise it by the power of x minus 1 divided by ln x. See, by the rules of exponents, these are cancelled because ln x divided by ln x is just 1. So right now this is just 0 to 2 e raised to x minus 1 dx. And lastly, since this is so easy to solve, this is just e raised to x minus 1, and from x equals 0 to x equals 2, which is now the answer, gives us the answer of e minus 1 over e. So this is the final answer for that problem. So if you enjoy the solution or this video, you may consider to subscribe. Please subscribe my channel, and don't forget to like and click the notification button so that you will be notified when I upload new videos. So thank you.